This video is going to talk about a NASA document describing the descent of the lunar module on the Moon. A link to this document is given in the description of the video. This is a schema included in this document showing how the lunar module joins the orbit from which it starts the powered descent. In fact, the lunar module does not start the powered descent from the orbit of the command module, for this orbit is too far from the lunar surface. It first reaches a closer orbit. How does it reach this closer orbit? It reaches it by following a natural orbit, but this orbit, instead of being at a constant distance from the lunar surface, is at a variable distance from it. On one end it touches the orbit of the command module, and on the other end it touches an orbit closer to the lunar surface from which it will start the powered descent. So how does it put itself on this orbit, called Hohmann transfer? For it is an orbit which allows to go from a circular orbit to another circular orbit which is at a different distance from the lunar surface. It does it by changing its orbital speed so that it corresponds with the orbital speed of the transfer orbit on the contact point with the orbit of the command module. The orbital speed of the orbit of the command module and the orbital speed of the transfer orbit can be computed with Kepler's law. According to the document, the orbital speed of the transfer orbit is 75 feet per second lower than the orbital speed of the command module's orbit at the contact point, and this is correct. It means that the lunar module must reduce its orbital speed by 75 feet per second to put itself on the transfer orbit. When the lunar module reaches the closer orbit, there must be a new maneuver to put the lunar module on the closer orbit. You might think that this maneuver consists in increasing the orbital speed since it has been decreased at start, but not at all, for the orbital speed of the lunar module increases along the transfer orbit. As it descends to the Moon, and it must again decrease its orbital speed by the same value to put itself on the closer orbit when it has reached it. The speed decrease is made in 3 steps according to the document. 1. A first maneuver which consists in throttling at 10% of the thrust during 15 seconds. 2. A second maneuver which consists in throttling at 40% of the thrust during 13 seconds. 3. A third maneuver which consists in an overburn, making the lunar module lose 12 feet per second in 3 seconds. Note that they don't say at what percentage of the thrust the third maneuver corresponds. The knowledge of the maximum acceleration or deceleration of the engine allows to check if this succession of maneuvers effectively allows to obtain the desired reduction of speed of 75 feet per second. We'll call this maximum acceleration m. When the first maneuver causes a decrement of speed equal to m by 0.1 by 15. 2. The second maneuver causes a decrement of speed equal to m by 0.4 by 13. So the total decrement of speed would be equal to m by 0.1 by 15 plus 0.4 by 13 plus 12 equals m by 6.7 plus 12. But do we have a way of knowing the maximum acceleration of the engine m? Yes, we have, for NASA gives the specifications of the lunar module. According to NASA, the LM had a total mass equal to 1500 kg for the HS Ares, the one of the first missions. The LM's engine had a force of 43900 newtons according to NASA. So the lunar module's engine, with full tanks and maximal thrust, could give an acceleration m equals 43900 divided by 1500 equals 2.888 meter by square seconds equals 9.627 feet per square seconds. So we can now calculate the initial decrement of speed caused by the engine's thrust. Speed decrement equals 9.627 by 6.7 plus 12 equals 76.5 feet per second. You'll say that it does not make much difference with the reduction of speed which must be applied, but a variation of 1 foot per second in the reduction of speed makes a variation of altitude of 1200 and 50 meters at the other end of the orbit, and this variation might make the powered descent fail. The final overburn makes the LM lose 12 feet/s in 3 seconds. With a maximum thrust, the LM would lose 12 feet per second, and 12 divided by 9.627 equals 1.246 seconds. It means that in the third maneuver, to reduce the speed of 12 feet per second in 3 seconds, the LM applied a fraction of the thrust equal to 1.246 divided by 3 equals 0.41, so 41%. So the third step uses the same percentage of thrust as the second step. Finally, we can see that the lunar module first throttles at 10%, then at 40% to have obtained the desired reduction of speed. Now, why does the way the speed of the LM is decreased make no sense? Because it starts with a low throttle, 10% thrust, and ends with a more important throttle, 40% thrust. It should have been the converse. The LM should have started to throttle consistently and more moderately at the end of the speed decrease, so that it could adjust the speed decrease as precisely as possible. Indeed, a variation of a simple foot per second at the start of the transfer orbit causes a variation of altitude of 1250 meters at the other end of the transfer orbit. So things have been made in reverse order. To give you a comparison, when you want to park a car after you are almost parked, you go at low speed to adjust your parking as well as possible. You don't do the converse. You don't first go at low speed, and when you are almost parked, you go at high speed to finish parking your car. Now, what excuse do they give to start throttling at 10% instead of 40% like they should logically have? They say that it is for a purpose of center of gravity trimming, which means that the guidance would try to adjust the gimballing system so that the thrust would be directed toward the center of gravity of the lunar module. Otherwise there is a misalignment torque which appears, and this misalignment torque makes the lunar module turn. All along the descent, as the propellant tanks are emptying, the center of gravity is shifting, and so the guidance acts on the gimballing system to reorient the thrust toward the new position of the center of gravity. But initially the gimballing system is pre-adjusted so that the thrust is directed towards the center of gravity when the propellant tanks are full. So there is no initial trimming to make. The gimballing system is supposed to have been pre-adjusted so that this trimming would not be necessary. It goes the same for the Saturn rocket when it lifts off. The gimballing system is initially pre-adjusted so that the global thrust is aligned with the rocket's center of gravity when the tanks are full. As the Saturn rocket burns fuel, the gimballing system is continuously adjusted so that the thrust remains aligned with the center of gravity. If the gimballing system was not initially adjusted so that the thrust is aligned with the center of gravity, the guidance would not have the time to make this adjustment. It would be set off balance, and would crash before it had a chance to do this adjustment. That's why when, in the movie, In the Shadow of the Moon, the astronauts Buzz Aldrin and Mike Collins say that, at liftoff they have felt the rocket sway because the gimballing system was looking for the center of gravity. It is total bullshit. This is a joke that the engineers have suggested them when they were in the hypnotic sleep under the control of the CIA doctors who were applying to them the mind control program, MK Ultra. The fact that Buzz Aldrin and Mike Collins repeat this nonsense proves that they were not in the Saturn rocket when it lifted off, for, if they had been in the rocket they would not have felt this swaying move they are talking about. Now they show this table of descent of the lunar module. This table contains plenty of hints which are going to be explained to you. They describe the operational phases of the landing, starting with the braking phase, which allows the lunar module to lose most of its important horizontal velocity. The lunar module indeed has a very important initial horizontal velocity relatively to the Moon of almost 6,000 km per hour, that it must absolutely lose before landing. Imagine what would happen if it was landing with such velocity. It would be literally pulverized. During the initial phase, the LM is oriented horizontally, because it must use the thrust of its engine to counter the horizontal velocity and make it decrease. Initially, the centrifugal force allows to counter the lunar attraction, which means that it does not need to be countered. Progressively, as the LM loses its horizontal velocity, the centrifugal force decreases, which means that the lunar attraction tends to more and more attract the lunar module toward the Moon and make the vertical speed increase. But during the initial braking phase, the vertical velocity remains small relatively to the important horizontal velocity, and represents only a hundredth of the horizontal velocity, or around it. So in this phase, the lunar module ignores the lunar attraction and consecrates the thrust of its engine essentially to decrease the important horizontal velocity, which means that it remains horizontal. After this phase, it starts turning to vertical in order to start countering the lunar attraction before the vertical velocity becomes too important, moderately at first, then more and more as the horizontal velocity becomes smaller and smaller, to end up completely vertical at the end. This descent is far from being as trivial as some imagine, for the lunar module must arrive near the lunar surface with both a moderate vertical speed and a moderate horizontal speed. If the lunar module arrives near the lunar surface with a too important vertical speed, it is as sure to crash on the lunar surface. There is no way that it can recover from this situation. On the other hand, if the lunar module arrives near the lunar surface with a too important horizontal speed, it is also doomed. There is no way that it can recover from this situation either. This shows that this descent requires a very good control, and that no error is tolerated in this descent. In this table we have the following columns. The column Event describes the current event. The column TFI indicates the time elapsed between the start of the powered descent and the current event. The column Inertial Velocity represents in fact the horizontal speed of the lunar module, and is indicated in feet per second. This velocity starts from the orbital speed of the lunar module. The column Altitude Rate is the rate of the altitude decrease and represents in fact the vertical speed of the lunar module. It starts from zero at the parking orbit, and first increases. When the lunar module starts fighting the lunar attraction, it then decreases. It is also indicated in feet per second. The column Altitude represents the altitude of the lunar module, that is its distance to the lunar surface. It is expressed in feet. The last command delta V, the triangle before the V, is a Greek symbol pronounced delta, and it is a mathematical symbol generally used to indicate a difference. Represents the difference between the speed that the lunar module would have if no thrust had been applied and the current actual speed that the lunar module has. It represents in fact the thrust, for it is the thrust which allows to obtain this difference. In the NASA document they explicitly say that the velocity could be acquired by the Doppler radar only from the altitude of 2,000 feet. That means that the Doppler radar was only allowing to acquire the velocities which are colored in green. The velocities which have been colored in red could not be acquired by the radar, because corresponding to an altitude above the limit of acquisition of the radar, 22,000 feet. But this is completely absurd, for it is precisely the Doppler radar which allows to acquire these speeds. The Doppler radar is not used from a given altitude, it is used as soon as the signal comes back. And, concerning the altitude radar, they say that it was only taken into account from the altitude of 39,000 feet. That means that the radar could only allow to acquire the altitudes which have been colored in green, and not those which have been colored in red. But once again it is absurd, for it is precisely the altitude radar which allows to obtain the altitude. In reality, the altitude radar is used as soon as the signal comes back, and not from a given altitude. For the next checking of the table, some explanations are needed. When a vehicle rides at a constant speed v on a distance t and during a time t, we have the relationship d equals v by t. And when a vehicle starts riding on a distance t at a speed v1, regularly accelerates and is at a speed v2 at the end of that distance, and rides during a time t, we have the relationships d greater than v1 by t and d smaller than v2 by t. If one of these relationships is not respected, there is an anomaly. Between the events which have been colored in blue, rotate to windows up position, and green, altitude update, there is a difference of time equal to 4 minutes 18 minus 2 minutes 56 equals 82 seconds. At the first of these two events, rotate to windows up position, the altitude rate is indicated as minus 50. At the second of these two events, altitude update, the altitude rate is indicated as minus 89. That means that the altitude rate is comprised between 50 and 89 feet per second between these two events. So the minimal lost altitude is equal to 82 by 50 equals 4100 feet, and the maximal lost altitude is equal to 82 by 89 equals 7298 feet. Now the difference of altitude between these two events is equal to 449343920 equals 5733 feet. 5733 is comprised between the minimum 4100 and the maximum 7298. We have computed from the rate, so we have a coherence here. If a normal situation has first been shown to you, it is to show you a less normal, more embarrassing situation. Between the two events which have been colored in blue, altitude update and green throttle recovery, there is a difference of time equal to 6 minutes 24 minus 4 minutes 18 equals 126 seconds. At the first of these two events, altitude update, the altitude rate is indicated as minus 89. At the second of these two events, the altitude rate is indicated as minus 106. That means that the altitude rate is comprised between 89 and 106 feet per second between these two events. So the minimal lost altitude is equal to 89 by 126 equals 11214 feet, and the maximal lost altitude is equal to 106 by 126 equals 13356 feet. Now the difference altitude between these two events is equal to 390124639 equals 14562 feet. So the actual lost altitude is greater than the maximum lost altitude, 13356 feet given by the altitude rate. Now we have a clear incoherence, a situation which is outright impossible. This is another hint that this table does not show a normal descent. Now we are going to get interested in the last column, the delta V. Like already said, the delta V represents the difference between the speed that the lunar module would have if no thrust had been applied and the actual speed, and it represents the thrust. In order to be able to check if the delta V which is indicated in the last column is normal, we have to know how to compute it. The delta V is a combination of a horizontal delta V and a vertical delta V. If no thrust was applied, the lunar module would keep its orbital speed. So the horizontal delta V is the difference between the orbital speed and the current horizontal speed. Concerning the vertical speed, if no thrust was applied, the lunar module would have an acceleration equal to the lunar gravity constant, g equals 1.622, which means that after an interval of time t, the vertical speed would be equal to the gravity constant multiplied by the time t. There is a division by 0.3 to convert the speed in feet per second. The current vertical speed is subtracted to this computed value to obtain the vertical delta V. Then the delta V is computed as the square root of the sum of the squares of the horizontal delta V and the vertical delta V, according to the theorem of Pythagoras. Now that we know how to compute the delta V, we are going to compute it at the event I gate. The current horizontal speed is 506 feet per second. The current indicated time is 8 minutes 26 equals 506 seconds, and the current vertical speed altitude rate is 145 feet per second. So the horizontal delta V is equal to delta VH equals 5560 minus 506 equals 5054 feet per second. And the vertical delta V is equal to delta VV equals 1.622 by 506 divided by 0.3 minus 145 equals 2590 feet per second. Now we can calculate the delta V. Delta V equals square root 5054 squared plus 2590 squared equals 5679 feet per second. But in the table of the powered descent, the current delta V is indicated as 5375 feet per second only. That makes a difference of more than 300 feet per second. It means that the thrust which has been applied by the LM's engine is not sufficient to obtain the speeds indicated in the table at this event. There must be a mysterious hidden force which has helped the lunar module to reduce this speed. What might be this mysterious force? Let's bet that it is Mickey Mouse's hand which has been very helpful. Now, let's take the event low gate. The current horizontal speed is 68 feet per second. It is the number between brackets. The other one is said being relative to the lunar surface. The current indicated time is 10 minutes 26 equals 626 seconds, and the current vertical speed, altitude rate, is 16 feet per second. So the horizontal delta V is equal to delta VH equals 5560 minus 68 equals 5492 feet per second. And the vertical delta V is equal to delta VV equals 1.622 by 626 divided by 0.3 minus 16 equals 3368 feet per second. Now we can calculate the delta V. Delta V equals square root 5492 squared plus 3368 squared equals 6442 feet per second. But the current delta V is indicated as 6176 feet per second only. That makes a difference of 266 feet per second. It is less than the previous difference, but still relatively important, more than 200 feet per second. Once again, the thrust which has been applied by the LM's engine is not sufficient to obtain the speeds indicated in the table at this event. So once more there must be a mysterious hidden force which has helped the lunar module to reduce this speed. Let's bet again that it is Mickey Mouse's hand which has been very helpful. Now, let's take the last event, touchdown. The current horizontal speed is 0 feet per second, the number between brackets. The current indicated time is 11 minutes 54 equals 714 seconds, and the current vertical speed, altitude rate, is 3 feet per second. So the horizontal delta V is equal to delta VH equals 5560 feet per second. And the vertical delta V is equal to delta VV equals 1.622 by 714 divided by 0.3 minus 3 equals 3857 feet per second. Now we can calculate the delta V. Delta V equals square root 5560 squared plus 3857 squared equals 6766 feet per second. But this time the indicated delta V is very close to the theoretical delta V and even slightly greater, instead of being consistently smaller like in the previous events, more than 200 feet per second difference, for it is equal to 6775 feet per second. So this time, the thrust has been sufficient to obtain the indicated speeds. Mickey didn't have to help the lunar module this time. So what happened? How is it that the final delta V could be so close to the final theoretical delta V when the previous values of the delta V were consistently smaller than the theoretical delta V? In fact, the answer lies in the document. They say this. In addition, 85 feet per second is added to assure 2 minutes of flying time in the landing phase. Also, the 60 feet per second of V is added for LBD operation in the approach phase to avoid large craters, 1,000 to 2,000 feet in diameter, in the landing area. This is highly hilarious, for the guidance makes precise calculations, and does not make such suppositions. It does not artificially increase the calculated thrust just in case there would be unexpected craters. This is a joke, and one hint more that this descent table makes no sense. For the last hint I must give some explanations. As the moon orbits the Earth counterclockwise, it also slowly spins counterclockwise so to always show its same side to the Earth as this simplified animation shows it. The last indicated horizontal speed precisely corresponds with the displacement speed of the lunar surface. It is indicated negatively if the lunar module lands in a direction opposed to the spin of the moon. If the indicated speed was absolute like the previous speeds are, it would mean that the lunar surface and the lunar module would move synchronously with each other, and so it would mean that the lunar module is stationary relatively to the lunar surface. And the lunar module must absolutely be stationary to the lunar surface when it lands, for, if it laterally moves relatively to this one, it is almost sure to tip over when touching the lunar ground, for it has no wheel and the lunar ground is uneven. And then comes the final trick. There is an annotation which says that the last horizontal speed along with the previous one is no more absolute like the previous speed, so the table would but is now relative to the lunar surface. So what does it mean? It means that instead of moving synchronously relatively to the lunar surface like it would have if the indicated speed had been absolute, it now has a lateral speed relatively to the lunar surface, which is equal to displacement speed of the lunar surface. This speed may not be important, 15 feet per second, that is 16 kilometers per hour, but at that moment the lunar module is at 4 meters from the lunar surface, and it ascends at a speed of 1 meter per second, which means that it will touch the lunar ground in 4 seconds. And it does not have the time during these 4 seconds to null this speed with its lateral thrusters, which are much less powerful than the main engine. So we are afraid that poor lunar module will tip over when it touches the ground. But Houston can care about this problem by sending an emergency crane by express service. This crane will be able to put the lunar module back on its legs. Seriously, the demonstration has been made to you that this document is nothing but a collection of jokes. These jokes are simply a way that the engineers used to make us understand that this descent never happened, and the lunar module never landed on the moon.